So, what you are looking at is a Helmholtz model, and the second one is a model which is proposed by Gouy and Chapman, is what is called as a diffuse double layer model. Okay. Can you look at and tell me what is the difference between the picture on the left and the right? The name says it all, diffuse, right. So, if you look at here, right, the counter ions, okay, they are, if I look at a similar distance here, right, I look at similar distance, the number of counter ions that you have, okay, for a particular distance, say in this case x and a similar distance x, okay, definitely the number of counter ions here are more compared to there, right, that you can get. And the fact that there are also counter ions here, you can say that the thickness of the double layer, now it is kind of a little bit expanded, right, it is a little bit more, right. So, it turns out that this picture is more true, okay, than what was, what comes out of Helmholtz model. The reason for that is that the Gouy-Chapman model, okay, what is also taken into account is the thermal motion of the ions. Okay. So, we are saying that of course, they could be bound to the charged surface. However, these ions can still exhibit thermal motion, they can be disturbed because of the thermal motion. These thermal fluctuations tend to drive the counter ions away from the charged surface. Okay. This leads to the formation of what is called as a diffuse double layer, which is extended more than a monolayer thickness. Okay. So, that is a prime difference between Helmholtz model and the Gouy-Chapman model, in which it is assumed that because of the fact that these ions exhibit thermal motion, these thermal fluctuations can drive the counter ions away from the particle surface, away from the charged surface, and the layer of counter ions is more diffused compared to what was the case for Helmholtz double layer model. Okay. Now, again similar to what we did for Helmholtz model, we are kind of interested to look at the distribution of counter ions in solution. Okay. So, we are interested in understanding distribution of counter ions as well as co-ions in solution, number 1. Number 2, we also want to understand what is the thickness of double layer. Okay. We would like to kind of get quantitative information of these quantities. Okay. So, for the diffuse double layer model, the starting point in obtaining the diffuse double layer model description is the what is called as a Poisson equation. Okay. Okay. So, we will think a little bit about deriving the Poisson equation to begin with. Okay. I am sure all of you know this, but we will try and use some very simple arguments to show that you can actually derive Poisson equation, because this is a starting step for looking at electrical double layer model. I thought it will be nice to do it. Again, it's in the textbook that I am following. Okay. So, this is a point charge plus q minus q, and the distance of separation is r, and the force that is acting between the two charges is given by this, right. It is the Coulomb's law, right, 1 over 4 pi epsilon naught q1 q2 or q square divided by epsilon naught, r into r square. That is the Coulomb's law. Now, if I somehow take this guy out, okay, if I take this out and ask a question as to if I have a positive charge q, okay, and I ask a question as to what is the electric field that is generated at some distance r from this charge q. So, that electric field is given by F c divided by q, which is 1 over 4 pi epsilon naught q divided by epsilon naught r square, right. Okay, we know that. Now, it turns out that, okay, so the expression that we wrote earlier, right, they are for point charges. Okay. Now, this expression holds good not only for point charges, for however, for any distribution of charges, such that the total charge is q. Okay. So, what I mean by that is, if I imagine that I am going to enclose this in a sphere, okay, of radius r, I will consider some distribution of charges. Okay. Now, if I have a distribution of charges, I can define again a charge density. Okay. I can define a charge density q, that is the number of charges or the charges per unit volume multiplied by the volume, right. If q, rho star is the charge density. Okay. So, what we are doing is, we are considering a sphere of radius r which contains q units of charge which are uniformly distributed such that the charge density is rho star. Therefore, this q, I can relate that to the volume of the sphere and the surface charge density. Okay. Instead of a point charge, if I replace that with a sphere with certain distribution, but as long as the total charge is q in this case as well as this case, the same expression would hold good. Okay. That is what I am trying to mention. Now that we have this, that is the electric field that is generated at some distance, okay, and at some distance r from a distribution of charges which has a charge density rho star, right. So, what we can do is, I can take this expression. So, I have E here 1 over 4 pi epsilon naught. Okay. So, I have epsilon r into r square here. Instead of q, I am going to replace q with this, right. Instead of q, I am writing this in terms of the surface charge density and the volume. Is that okay? Okay, that just comes from the definition itself, right. So, we had done this here. I mentioned that the electric field that is generated because of the point charge, this expression gives you the electric field that is generated because of the point charge which has a charge plus q, or the same expression would also hold good if I replace the point charge by certain distribution of charge such that the overall charge is q. Okay. That is given by the volume multiplied by the surface charge density, right, or the charge density itself. Okay. Instead of q, I am replacing that with 4 by 3 pi r cube into rho star. Is it okay? Now, that is, yeah, go ahead.
Volume density.
So, this is rho is what is called the charge density. This is the if I say that there are 100 charges, okay, which are uniformly distributed, 100 ions for example, say, uniformly distributed. That is an assumption. Yeah, and then the charge density is going to be 100 multiplied by 1.6 into 10 power minus 19 coulombs divided by the volume.
Okay. And no, otherwise that center of charge.
Yeah, you have to worry about. If the distribution is not uniform, then
So we are assuming that
it's a uniformly distributed charge. Yeah. So, therefore, here I can cancel r square with here, okay, that leaves me r in the numerator and rho star here, and the 4 gets cancelled, okay, and the pi gets cancelled. What you have here in the is a 3 that comes from here, and epsilon, where epsilon is epsilon naught into epsilon r. Okay, therefore, this E, therefore E becomes r rho star divided by 3 times epsilon. Now, what I can do is I can take this expression, I can multiply by r square on both sides, okay, and then I am going to differentiate that with respect to r, okay, d by dr, right. So, therefore, this d by dr of r cube into rho star by 3 epsilon. Okay, so, therefore, this becomes 3 r square into rho star by 3 epsilon. This gets cancelled. So, essentially I am left with r square into rho star by epsilon. Okay. So, therefore, now that I know that there exists a relationship between the electric field and the surface potential, left hand side is going to remain the same, d by dr of r square into epsilon, that comes from here, right, and the right hand side is going to be r square rho star into epsilon, right. That is what we just derived. Now, instead of epsilon E, I am going to replace that with d psi by dr, right. I am going to replace that with d psi by dr, and because I have a negative sign here, so I am going to get minus on the right hand side or left hand side, okay, depending upon how you want to do it. Okay. So, therefore, essentially I end up with d by dr of r square d psi by dr is equal to minus r square into rho star divided by epsilon. I can get this r square into the other side. Therefore, 1 over r square d by dr of r square d psi by dr is equal to minus rho star divided by epsilon. Okay, that is what you. Okay, so that is essentially. So, now in this case what was assumed is that the charge, right, it the so if you, that's a is a so I want to go from, if you look at this, right, the same thing is written in a partial derivative form. Okay. So, because you could have a case where psi need not be varying only with respect to r. You could also have a case where the psi, the surface potential, can be a function of both theta, phi as well as r, right. So, what we derived is the first term in the equation. Similarly, if you assume a variation only in theta or variation only in psi, okay, and if I take a general case where psi is a function of both r, theta and phi, okay, so you end up with this expression. The left hand side can be written as del square psi, and the right hand side is essentially minus rho star by epsilon. Okay, this is what is called the Poisson equation. Okay, what this equation essentially tells you is that if I have a surface which is charged, okay, if I have a surface which is charged, how does the potential vary with distance, okay, in different directions. Okay, that is what this expression essentially tells you about. Okay, so, now with this Poisson equation as a starting step, we would like to look at potential near a planar charged surface. Okay, so, what we derived was a case where I have a spherical surface, okay, and what is the variation of surface potential with r, theta and psi is what we looked at. But if I look at because the calculations are much more easier if you work with a planar charge surface, we would like to look at we would like to start with Poisson equation. In the case of a planar surface, the Poisson equation becomes del square psi by del x square plus del square psi by del y square plus del square psi by del z square is equal to minus rho star divided by epsilon. Okay. And so basically the Poisson equation essentially tells you something about the variation of potential with distance from a charged surface. Okay. It could be for any arbitrary surface. Okay. That is what is described by the Poisson equation. Okay. And this del square is what is called as the Laplace operator, so you know a little bit about it, right. Now what we would like to do is we would like to solve this, right, because if I want to find out what is the how does this we know that this psi is a function of x, y, z. I would like to look at the variation of psi as a function of x, y and z. So for that we would have to solve Poisson equation. Okay. And what we are going to do is epsilon is epsilon r multiplied by epsilon naught, which accounts for the presence of the medium, and rho star is the charge density. Units are coulomb per meter cube. Okay. And of course psi is a function of x, y and z. Okay. So the objective is to find the potential. The objective is to find a potential that satisfies the Poisson equation, and with the boundary condition that at x is equal to 0, sorry, at x is equal to infinity, when x is tending to infinity, psi is going to be 0, right. If I have a charged surface, if I look at a distance very far away from the surface, the potential is going to be 0. That is one of the boundary condition. Okay. And the potential at the interface, okay, that is when x is equal to 0, the potential is going to be psi naught. Okay. These are the two boundary conditions that we are going to use. At x is equal to 0, the potential is psi naught. At x is equal to infinity, psi naught is 0. Okay. So therefore we would like to obtain an expression for the potential that satisfies the Laplace equation with these two boundary conditions. Is that okay? Yeah. So now, so how do we do that? So I want to solve this. So we are going to okay. So what you looked up here is an expression where we see that the potential varies with x as well as y as well as z. We are going to take even a simpler case. We will only talk about the one dimensional case, okay, in which the potential varies only with x. So therefore I can write this as d square psi by dx square, right, that is equal to minus rho star by epsilon. So what we are looking at is we consider a planar solid surface with homogeneously distributed electric charges such that the density is rho star, that is in contact with a liquid. Okay. And as a result of the charges on the surface, okay, the surface generates a potential which is what is called which is represented as psi, okay, and this psi would vary with distance in some particular way, where after calculating what this function is, we would like to find out whether psi of x is it an exponential function, okay, does it vary exponentially as we move away from the surface, or does it vary linearly, okay, does it have any other functional form. That is what we would like to look at, right. The objective is to obtain an expression for the potential distribution. So for that we are going to consider a one dimensional Poisson equation. Okay. Now in order to do this, right, so psi is a permittivity, right. So, that is going to be, if I am going to do an experiment in a liquid which is maintained at a particular temperature, and if the medium, I know everything about the medium, your epsilon is going to be a constant, right. But however, this sigma star, okay, so in order to actually solve this, I should somehow express rho star in terms of the potential itself, right. That is when I can solve this expression, right. To solve this expression, the charge density, that is rho star, has to be expressed as a function of potential, right. Only then, if I have a way of writing, right, rho star, I would like to express rho star as a function of psi itself, then I can substitute for rho star. I can go ahead with solving this, right. So, to do that, what we do is we use something called as a Boltzmann factor. Okay, we use something called as a Boltzmann factor. So, what is written here is Ni is the number of ion types, okay. I is the type of the ion that I am considering, okay, number of ion types per unit volume. So, units of this is going to be number per volume, okay, near the surface, okay, and Ni infinity is the concentration of the ions at a distance very far away from the surface. Again, this is going to have units of, again, number per unit volume, and Zi is the valency of the ions, and E is the charge of the electron, psi is the potential, and kBt is the thermal energy, okay. So, that is the Boltzmann factor, okay. So, what this expression essentially tells you is that, so this tells you something about, given that I have a surface potential, okay, given that I have a surface whose potential is psi, okay, what is the probability of finding an ion, okay, with a so there are going to be several ions, right, in the solution. There is going to be several ions in solution, okay. Now, so if you look up this, so let me just go through this, okay. So, what this tells you is that, the work required to bring an ion from infinity to a position at which the potential is psi. So, say that I have ion, say Ni, okay, at a distance very far away from the surface. Now, to move this ion from a very large distance away from the surface into a region very close to the surface, I have to do some work, right. Does that make sense, right? I would have to essentially do some work to move any ion from one location to the other, okay. How much of work that I have to do depends on from where to where I want to move it, right. If I want to move it to a distance very close to the surface, I may have to spend more energy, but if I am okay to move it to a location which is slightly away from the surface, I would have to spend less energy, right. So, this work that has to be done in moving the surface, in moving an ion, is essentially given by Zi times E times psi. This psi would be the potential at any location where you want to move it, okay. The psi is the potential at a location where you want to move the charge, okay, and it will depend also on the valency of the ions itself, right. If Zi, whether I have a monovalent ion or a divalent ion, it also depends on that, okay. So, the probability of finding an ion at this position is related to the ion concentration at infinity. Okay, this is the ion concentration at infinity, okay, through this Boltzmann factor. Think a little bit about this. So, we will again discuss the Boltzmann factor in the next lecture, and then we will try and proceed with obtaining a solution for one dimensional Poisson-Boltzmann equation, Poisson equation. Okay, we will try and do that in the next class. Okay, yeah, thanks.